So it's basically in section 1, we just learned how to plot a vector, how to find direction, magnitude, and unit vector. We didn't really do any actual motion problems, except maybe one sort of motion thing where we did a unit vector. But here is the first example right here. The particle moves on the xy plane with position vector 3t squared minus 4 cos t and t times e to the negative t. So if you're going to find the velocity vector, you're just going to take the derivative. Okay? All right, so this shouldn't be hard. Just keep the brackets here. The derivative of 3t squared is 6t. The derivative of negative 4 cos t is plus 4 sine t. Comma. For this one, you're going to need product rule. So you're going to have derivative of t times e to the minus t plus, and then t times the derivative of e to the minus t, so negative e to the minus t. There we go. Okay, so the velocity vector is officially 6t plus 4 sine t, comma, and let's factor out that e to the minus t. Okay, so there's our answer. Right there. Acceleration vector, you just take the derivative again. Not very complicated. So it's going to be 6 plus 4 cos t, comma, and then you're going to have to do the product rule again here. So I'll do that in blue over here. The derivative of e to the minus t times 1 minus t plus e to the minus t times the derivative of 1 minus t. So this just comes out to be e to the minus t times t minus 2. I already factored it for you. Okay? All right, so velocity vector and acceleration vector. Okay, let's talk about what these mean real quick, including the position vector at the top. So what is this thing I gave you right here? What is this at the top, r? What is that thing? So when I give you r of t, this is basically the description of a vector arrow that has variable components. So in other words, if t is 0, this comes out to be whatever, negative 4, comma 0. Okay? If t is 1, it comes out something else. If t is 15, it comes out something else. So it's a variable position, I guess you could say. So the job of that first vector I gave you, r of t, is to sort of help you find the position of the object. Okay? So r of t points from the origin to the actual point. Okay, so let's just say that this object's moving around on the xy plane, and it's a red, I don't know, it's like a little red ant. It's a red ant, fire ant, crawling around on the xy plane. R of t's job is to tell you how to go from the origin to that ant. Okay? So that's the vector r. By the way, this curve is not this particular curve. I'm just trying to explain what r means. So r is a vector that leads from the origin to the fire ant. Okay? V is the vector that represents the velocity of the fire ant. So it would be this vector right here. This thing tells us which way the fire ant is moving, and that v vector should always be tangent to the curve. Okay? So the v vector is always tangential to the path that you're on. And lastly, the acceleration vector, I'll draw that in blue. The acceleration vector that thing's job is to help us understand what kinds of tendencies the velocity is going to have. All right? So how many of you remember that force is equal to mass times acceleration? You guys remember little hard to understand what an acceleration vector's meaning is, but at least understand the r and the v vector, okay? All right, so since we don't really know what this path looks like, I couldn't draw this path, but I can explain what these mean. All right, but that problem's done because they didn't ask us to do anything else. Let's go to the next one. So example 2 has a ton of parts to it, but the math isn't hard. So the first thing they ask for is the acceleration and velocity vectors. So we're going to do the exact same thing we just did. So the velocity vector is going to be dx dt, dy dt, right, for the first derivative of position. In other words, e to the t minus e to the negative t, comma, e to the t plus e to the negative t. The acceleration vector, that's the second derivative of position, both for x and y. So you take the derivative again. So I'm assuming you're comfortable taking the derivative of e to the something. So these are our two answers. So we're already done with part A. That wasn't hard. Okay, and then it says find the velocity at t equals 0. So you already have the vector, just plug in 0 for t. So the velocity at 0 would be e to the 0 minus e to the negative 0, comma, e to the 0 plus e to the negative 0. In other words, basically 1 minus 1, 1 plus 1. It looks like my velocity vector is 0, 2. 0, 2. Please understand this is an instantaneous velocity. So we are happening to be talking about time 0. At any other time, this vector would be different. That's very important to understand. It's not like constant velocity situation. There is one instant where the velocity is 0, 2. This might be the only instant. But what does it mean to have an x velocity of 0 and a y velocity of 2? Up or down, which is it? Up. Yeah, this means that the object, right, is traveling along on the xy plane, and at this instant, which happens to be the time 0, it's moving straight up at that instant. Does that mean that the object's going like this, straight up the page? Only at that instant. Okay? At t equals 1, it might be doing something else. It might be going down, or left, or right, or both. You know? Okay, so anyway, that's your velocity vector for time 0. You can put units on meters per second, meters per second. But this one I'm just interested in units. What is the acceleration at t equals 0? Well, let's plug our 0 into our second function. E to the 0 plus e to the 0, e to the 0 minus e to the 0. So this is interesting. This is giving us 1 plus 1, 1 minus 1. In other words, 2, 0. What does this mean? Well, if the mass of the object is 1, you can think of this as a force. So this is kind of like it's being pulled with 2 hidden force to the right. And there's no upwards or downwards pull. Okay? So I like to think of acceleration as forces. I just pretend the mass is 1. It helps me kind of understand what that 2, 0 means. The object is being pulled to the right, but not up or down. Just at the beginning of the motion. Okay, so we've got a few facts we're going to put into a graph at the end of the problem. Let's go on and answer part D, so I'm going to erase this. Everything's very formulaic. We're just going to try and understand the questions too, like what it all means as we go. Describe the motion as t goes to infinity. Okay, so we have three vectors. We have r of t, which was e to the t plus e to the minus t, comma e to the t minus e to the minus t. We have the velocity vector, which was e to the t minus e to the negative t, comma e to the t plus e to the negative t. And we have an acceleration vector. So you guys tell me which vector here would best describe the motion. If you were asked to analyze the motion or describe the motion, which one's probably the best one to explain the motion? It's a bit of a trick question, but which one, if somebody says, hey, can you tell me what's going on with that car over there? You'd probably describe which of these. Would you explain where it was, how fast it's going, or how fast its speeds are changing? How fast it's going? Yeah, the velocity has a nice way of just presenting what's going on. If you tell me which way something's moving and how fast it's moving, that's pretty much a good description of its motion, right? If you said something to somebody like, oh, that car's acceleration is always positive, not everybody even knows what that means. But if you say, hey, the velocity of that car is just continually increasing, everybody knows what you're talking about, right? So I think we should try to describe V here as t gets very large. Okay? So we're voting on V to help us describe the motion. Okay, so we're going to stick with V here. And we're going to let t get very large. Okay? So I'm going to do a couple of things. I'm going to do limit as t goes to infinity for the velocity vector, which means I'm going to do an LIM t goes to infinity for this expression. This is just 1 over e to the t, comma, LIM t goes to infinity e to the t plus 1 over e to the t. So I'm doing the limit as t goes to infinity of velocity. I'm trying to understand what's happening to the speeds as we let t get big. Okay, so what happens when I let t get large? 1 over e to the t vanishes, that's true. But the e to the t grows without bound, right? So basically we get infinity in both of these expressions. So this part, you could say, becomes insignificant. But we basically get this. The vector infinity, infinity. What in the world does that mean? Remember, this is meters per second, right? If this problem is done in the standard units. So what does it mean for something to have infinite speed rightward and infinite speed upward? How would you describe that motion? Unstoppable. Forget what Einstein said about infinite speeds, okay? He said that's not possible. He did. The speed of light is the maximum. Anything, carrying information. But my point is on this, what's happening to the speed? It is growing, what? Without bound, right? So what I wrote on this problem was the speed in both the x and y directions is increasing without bound. Now, is that a good description of the motion? To say that the speed is increasing without bound. Is that a good, full, solid description of the motion? What can you not picture? If I told you, I'm thinking of an object and it's going really fast and it's getting faster and faster, what do you still not know about the object? Its direction. Our goal was to describe the velocity, right? That was what we decided we were going to do. We never described the direction. Okay, so here's what I need to do. I need to compare the two velocity components to check the angle at which it's going at. So remember the rule that to find the angle, you use inverse tan velocity y over velocity x, like that. In other words, inverse tan of e to the t plus e to the minus t all over e to the t minus e to the minus t. And we're talking about letting t grow without bound. So there's still an LIM t goes to infinity here. We're trying to describe the direction of travel as t gets infinitely large. Okay? They told me to discuss the motion as t gets big. I'm using a limit to do that. Okay, tan inverse is a nice, clean, one-to-one function. It rises monotonically. I don't know if you remember its graph, but it's basically kind of just rises. It's always rising. Which means I can just take this limit and put it on the inside. So I'm going to do tan inverse of the limit of, instead of limit of the tan inverse of. Okay, so I'm going to switch these around. And I'm going to put the tan inverse on the outside and the lim on the inside. Can't do that with every function, but you can do that with a monotonically increasing function of this sort. Okay, what is this inside limit? 1 is correct. It's 1. And what is inverse tan of 1? Pi over 4, or in vector world we often will use degrees. We don't use it for the calculus, but we use it to describe the motion. So I'm going to make my sentence a little bit better now. I'm going to say that the speed in both the x and y directions is increasing without bound. The object is moving in the direction of 45 degrees. So the object is approaching the 45-degree direction. Yeah. Yeah, it kind of is important. We're not saying that the object is traveling on the 45-degree line. What we are saying is that it's trying to travel on the 45-degree line. See, all of this happens when you reach infinity. When you actually get to time infinity, that's eternity. When you wait in eternity, you'll see it going in the 45-degree direction. Okay? So that's why I use the word approaching. As we'll see in a minute, this object is increasing its speed without bound. And it's trying to go in the direction 45. It never quite achieves it. We'll see that in a second on part E and F. Okay, so here's my takeaway, okay? Listen, they asked me to describe motion as t gets big. I chose to use velocity. I felt like that would give me the best way of explaining what's happening. It's not enough to give just the limit as t goes to the velocity function, or vector, but also the direction, so that we can clearly see which way it's going and that it's increasing its speed. That makes sense. So I actually have 2 limit calculations here, and all of that is critical thinking, because I was just told to describe the motion. So I just did 2 limits. Okay, but you could do the same. Just model your work after mine, if you see that question on the AP test. Show that the particle travels along the hyperbola x squared minus y squared equals 4. That's a very interesting question. And then we'll sketch the path and find a distance. So I'm going to zoom out so you can kind of see all 3 questions together. Okay, I was told that x was e to the t plus e to the minus t, and I was told that y is e to the t minus e to the minus t. I was never told to get rid of my t on this problem. But you'll notice something. If you add these 2 equations together, you might say, why would you do that? Well, I'm trying to actually get t out of this problem and just get an xy equation. Look what they're asking me to do. They want an xy equation, see? So I'm going to add these 2 together. Let's see what we get. X plus y equals what? 2e to the t. Okay. Now let's try subtracting these 2 equations. What will subtracting these equations cause to happen? Yeah, I'm going to actually have this term cancel this time. See? So I'm going to get this now. X minus y equals negative 2e to the minus t. And you'll notice that they asked me to find x squared minus y squared. So how can I use x plus y and x minus y to create x squared minus y squared? It should be positive, sorry. My bad. I don't know what that negative's doing there. Thank you. I'm looking to find x squared minus y squared, right? X squared minus y squared. I've got x plus y and x minus y. So what can I do with my two little equations I've created? Multiply them. It is fair to multiply equations together. We don't do it often, but you're welcome to do it. So let's multiply our two equations together. And we get x squared minus y squared equals 4. Bingo. Okay, so what does this mean? Well, maybe you haven't graphed a hyperbola in a very long time. Okay? If you were with Mr. Lynch last year, which you most likely were, you probably didn't graph hyperbolas with him. You graphed them in Algebra 2 the year before. Maybe a little with Mr. Lynch. So let's review that. First thing is, we don't usually have a 4 on the right. We usually have a 1 on the right. So we actually divide by 4 here, here, and here. Okay, this is called the standard form of a hyperbola. You can tell it's a hyperbola because it has that minus in the middle. The center is at 0, 0. And the reason for that is this just says x squared and y squared. So it doesn't say like x plus 5 squared and y minus 5 squared. That would have a center negative 5, 5. This has basically x minus 0 squared, and this is y minus 0 squared. In other words, everything's centered nicely at the origin. And sometimes it's kind of a challenging thing to figure out the a and the b distances on a hyperbola. But look, they're both the same. They're both 4. So this makes for very easy plotting. Basically what we're saying is, if you go right 2, up 2, left 2, down 2, this forms that box we would draw, remember? I've done this in a long time. This box looks like this. And then you're supposed to draw 2 diagonal lines. Represent the asymptotes there. And then the hyperbola either opens like this blue one here, or it opens like this red one. Does anybody remember how to tell which one it is? Is it the red one or the blue one? There's two possibilities here. Yes, it has to do with which term is positive, x or y. So in this problem, x is clearly the positive fraction, so it's actually the red one. Okay? It's just been a very long time since we've done this. This is about as hard as it gets for graphing conics on the AP test. That's why we didn't spend a ton of time on conics this year. It's pretty simple. You could also just pick a few x's and pick a few y's, and you could kind of map it out. Okay, there's our graph. Now, it asks us to include a velocity and acceleration vector at t equals 0 and t equals 1. So I think it'd be worth our time to find r of 0, so we know where the object is at the start, v of 0, so we know which way it's going, and a of 0, because they asked us to. They asked us to graph that. You know, I never did find r of 0. Yeah, you'll notice that the r vector was e to the t plus e to the negative t, comma, e to the t minus e to the negative t, and the acceleration vector was the same thing. So the blue and the black there are exactly the same thing. So I think we found this vector earlier was 0, 2, remember? And we already found this vector was 2, 0. And the r vector is exactly the same vector as the a vector, so that's 2, 0. So remember, this means where, this means velocity, and this means tendency. Right? Sorry, it's a little hard to see there. I'll write that on the right. The black is the where it is. The red is the how fast it's going and which way, right? So velocity. And the blue is sort of its tendency, or if the mass is 1, it's our force, our push or our pull on the object. Okay, so where is the object at the start here? At t equals 0, where is the object? At 2, 0. Okay, so I think we should plot that point right there. That is our starting point of motion. It started here at t equals 0. That's right. Okay, what is the velocity at time 0? 0, 2, which means straight up. We should draw that vector, and we should draw it straight up from this point, tangent to the curve. So I'm drawing a little vertical arrow here. This is my velocity at time 0. And the acceleration vector is right here. So if you're not in physics class, you might say, I don't understand the blue arrow at all. What is that thing? That's sort of, at this instance, imagine this is like an electron, and there's a proton over on the right side pulling on it. So that blue arrow represents sort of the draw, the pull that this green thing's feeling. Okay? But anyway, it turns out, you can see, that for all positive times, the only branch of this entire hyperbola that makes any sense at all is this upper right-hand branch in quadrant 1. In other words, all these other red pieces mean nothing at all. They're either for negative times or something weird. So let's erase them. We don't need all of these. We don't need a cluttered picture. We need a picture we understand. We don't even need quadrants 2, 3, or 4 at all. This is all we need. Evidently, the object is doing this. It's leaving the point 2, 0, and it's traveling along this curved path. That's what it's doing. Okay, it's going to take that route. At time 0, it is going straight up. There's actually a vertical tangent right there. The object starts off by just rising, like a helicopter off the ground. And then it goes off to the right. So it goes up and over. Why is it over? Well, it's being pulled that way. See the blue arrow? So it's rising from the point 2, 0. It's rising with the speed of 2, and its tendency is being pulled to right 2. So it's accelerating to the right by 2. So somebody, first grade, really didn't understand, like, I don't understand how I can have a horizontal acceleration if it has no velocity. Well, just think of the blue as a pull. So think of something that can be pulled. Right? It will respond. It just doesn't have time to move. It's still t equals 0. It hasn't moved yet. But it does go off to the right. See that? That's because of the blue arrow. Okay. So there's your drawing for t equals 0. They also ask for t equals 1. See that? So this is where we're going to need a calculator. At t equals 1, the object is probably going to be up here somewhere. You understand? At t equals 1. It's going to be right here somewhere, and we'd like to know that vector. How long is it? Which way does it point? Okay. I can tell you one thing. The velocity vector is going to be easy to draw, because the velocity vector is just always tangent to the path it's traveling. I'm going to draw a fairly long arrow for v of 1. This long black arrow means the object is moving quite fast already. We'll find out how fast in a minute. It is pointing in this direction because it's tangent to the path. You always draw a velocity vector tangent to the path you're on. Okay? As for the a vector, I'm not too sure yet. The blue one, I'm not quite ready to draw a of 1. Let's calculate it first. Okay? So we need some scratch room here, so let's see here. Let me just open a blank sheet. I need v of 1 and a of 1. And a calculator. Okay, so to find v of 1, I need to do e to the first minus e to the minus first, comma e to the first plus e to the minus first, like that. In other words, what's e minus 1 over e? I need a calculator. Okay? And I just loaned mine out, I think. So I'll have to trust my notes here. Please correct me if I'm wrong, but I think it's 2.350, comma, 3.086. Can someone verify that? That look right? 2.350? Okay. The acceleration vector is the other way around. It's e to the 1 plus e to the minus 1, comma, e to the 1 minus e to the minus 1. In other words, it's just 3.086, comma, 2.350. Okay? So I just kind of calculated those on a separate piece of paper because I was running out of room. Remember, these are run and rise, right? So the red one has about 2.3 units of run and about 3.1 units of rise. The blue one has 3 units of run and 2.3 units of rise. So it's not quite as steep, you see. So I'm going to go back to my other picture. Okay? And I'm going to go ahead and sketch in a less steep blue vector. Right here. Same length though. That's A of 1. So what's going on at time 1? Well, the object's over here now. We can actually find position 1. The velocity is sort of almost in the 45-degree direction. And the tendency is still to go upwards and to the right. See the pulling arrow? Acceleration arrow. It's pretty much the same thing as the force arrow if mass is 1. Okay? How far did the particle travel between times 0 and 10? That's just straight up calculator. You're going to use the distance formula I gave you on your sheet. So you're going to integrate from 0 to 10. The square root of okay, now what goes in here is dx dt and dy dt. In other words, the two velocity components. See right here, this is the same formula we used back in section 10.1. Okay? So we're going to put in the red components, e to the t minus e to the negative t, e to the t plus e to the negative t. This is velocity in x direction. This is velocity in y direction. Notice that we're squaring the first derivative. Those are not second derivatives. Okay? But if you run that on your calculator, you get a ridiculously large answer, 31,148.929. What is going on here? This is kind of when you stop and say, did I do that wrong? Why am I getting such a ridiculously large answer? Well, can someone tell me what this means? Yeah, we've got an object which is approaching an infinite speed, we said, right? We've given it 10 seconds to travel. So it starts here and it's traveled for 10 seconds. Okay, it started out going straight up and then it took off in sort of the 45-ish degree direction. And by the time you reach 10 seconds, this thing has already traveled 31,000 meters. Inches or whatever the units are here. So it's gone very, very far in only 10 seconds, and that's because the velocity increases without bound. So this is a very holistic problem. It has every element of AP exam in it. Okay? It's got the distance traveled. It's got all three vectors here. You can kind of see what the arrows all mean, hopefully. Probably the least important one is the black R vector, because it's just position. But the red and blue are super important to them, and they understand them. So I've got to relabel this E of 0, A of 0, B of 1, and A of 1. Everything's sketched. Notice that when a vector is larger magnitude, we actually draw it longer. This is so important. If you're not in physics, do have to sketch pictures sometimes for the free response. You actually have to grab and label things, just like I did. Okay? Step E, that's a lot of critical thinking. How did I know to do that? Add them and subtract them and multiply like that. I saw an x squared minus y squared, and I knew that was x plus y times x minus 1. That's how I knew to add the equations and subtract the equations and have an expression for each. If you've done a lot of SAT stuff, this stuff's easy for you. If you haven't, this is going to be very challenging. Step E. Okay, I'm done for today because there's more. There's like 2 more examples, but I can do those tomorrow. And this should get you through some of that FRQ stuff. Okay, so start on that.